Welcome to another episode of Bull with Boone. Today I'm going to discuss force, the strength of forces, and specifically electromagnetic force versus gravity. There are four known forces in nature. They suspect there's a fifth one, but that's still speculation, still being tested, trying to find it. And they use the Large Hadron Collider in CERN in Switzerland to do all the experiments. But in any case, there's four forces of nature. Let me write them down. Okay, so these are the four forces of nature, the four known forces, and those are all the forces. Anything else like glue or things that hold things together is all composed of these forces here. What I'm going to do is I'm just going to do a comparison quickly to show you the strength of these various forces. And what I'll do is I'm going to focus on electromagnetic force and gravity. So I'm going to let's call electromagnetic force a strength of 1. Therefore, the strong nuclear force actually turns out to be 137 times stronger than the electromagnetic force. The weak nuclear force is about 1 million times less than that. So the weak nuclear force is 0.000137, the strength of electromagnetic force. And then finally, then gravity would be, compared to electromagnetic force, 8 times 10 to the minus 37. So you can see they're very small values. Okay, now to compare these two forces, I'm going to use two formulae. So I'll write down the formulas quickly. So force equals. Okay, so these are the two formulas I'm going to use. So what I'm going to do is I'm going to let this one equal this one. So this is the same force. Then we can compare the two. Then what I'm going to do is I'm going to, for the force of gravity, I'm going to use the mass 2 will be Earth, and R2 will be the radius of the Earth. So basically, it's the force that any of us are attracted to the Earth. And for the electromagnetic one, these charges, what I'm going to do there is I'm going to take a minute drop of water, the size of a pinhead, 1 millimeter by 1 millimeter by 1 millimeter cubed. So, and I'm going to put them a meter apart. So you've got a small, this is exaggerated now, small drop and small drop in the traction. So there's going to be 2 drops of water, which is going to be a small, little, about the size of a pinhead, and I'm going to put them 1 meter apart. And then we're going to see how the strength of these two, and then I'm going to relate it to the force of gravity. So now what we do is we let this one equal this one here. Okay, so here I let these two forces equal each other. Now I rearrange this formula so that I get mass 1 on the one side. And so by having mass 1, we have something to visualize how strong this force is on gravity. So the force between the two water droplets, these small little water droplets, is going to be based on mass 1. But you'll just follow here. Okay, so we have now mass 1 is equal to the constant K, Q1 times Q2 over R squared. So we take R across here, and we take G across. Now since G is above the line, so it'll go below the line here. Mass of the Earth, we bring it down here, and that is R squared from there that stays there. So now we have M1 equals this. Now we'll work with this formula now. Okay, so what I'm going to do now is I need to calculate these two Q's. So I'm taking this 1 cubic millimeter of water. which is a microliter, not a milliliter, it's a microliter, a millionth of a liter. And I'm taking this little bit of water, and theoretically or hypothetically, I'm going to strip out all electrons. So in this water, this H2O, there is only protons. So this is how the calculation goes. What I'm also doing here is all my values I'm going to work always to 3 significant figures. So although this is 18.01 something something something, and this is 0.022 something something something, I'm just going to use 3 significant digits each time. So it makes our calculations and everything much easier. Okay, so we have here 1 mole of H2O of water contains so many molecules, 6.02 to the power 23 molecules. This is known as Avogadro's number. This guy worked out that 1 mole of a substance contains so many particles, whether it is molecules or whether it is atoms. But that's Avogadro's number. Then 1 mole of water happens to weigh 18 grams. That is because the atomic weight, H2O, consists of 2 atoms of hydrogen and 1 atom of oxygen. Atomic number of 8, but it's atomic mass of 16, just below 16, but call it 16, and 2 here gives you 18, and therefore 1 mole of water weighs 18 grams. Therefore, 1 gram of water contains 6.02 . So 1 gram of H2O contains so many molecules divided by so many grams. So it's per gram, there's so many molecules. Now, each molecule of water contains 8 protons from the oxygen and 1 proton each from the hydrogen. That's 10 protons. So 1 gram of H2O contains so many molecules times 10 to get protons. So it equals so many protons. Okay, so now we have 1 gram of water contains so many protons. But remember, we're not working with 1 gram, which is 1 milliliter. We're working with 1 microliter, which is 1,000th of that. So we divide this by 1,000. Now we'll put all these values. I'll just do our constants K, G, and these values I'll just put on the board here. Okay, so now here we have all the values we're going to work with. K is that value here. Q1, that is the charge on 1 proton, and then we must multiply it by how many protons we have. Okay, now we can put these values into our formula. So K. Okay, so the formula is K, value of K. Then this is the charge Q1, which is the charge on the electron or proton, which is the same charge, multiply molecules times 10 protons. Now all this must be squared because it's Q1 times Q2, and they're both going to be the same. So it's Q1 times Q2. And then the radius of the Earth. Multiply by that. And then we divide by the constant g here. And we divide by the mass of the Earth here. And the radius, the distance between the two little droplets of water, minute droplets of water. And that equals, use my calculator and work it out. Okay, so that equals 2.71 times 10 to the 12 kilograms. Okay, so this is the figure we're going to work with now. Okay, so what we've achieved here, we've rearranged our formula so that we have a particular mass. And if that mass weighs so much, that is the same force as 2 drops of water, 1 microliter, which is a bit bigger than a pinhead, 1 meter apart. So the force of these 2 droplets of water, assuming that these 2 droplets of water, we have stripped all the electrons off, so they both only contain protons. So it's actually a repulsive force because they're both positive, but it's just a negative that will be attractive. So the one could just be electrons, but the fact is 2 droplets of water, 1 meter apart, only consisting of protons in that small volume, 1 cubic millimeter. The force is equivalent to 2.71 times 10 to the 12 kilograms if we had to convert it into a mass, pulling you down onto Earth. Because we've used the radius of the Earth and the mass of the Earth, and we've rearranged the formulas. And that turns out that force is equivalent, so many kilograms is equivalent to a block of iron. A block of iron, 700 meters by 700 meters by 700 meters. In other words, a block of iron, 700 meters wide, 700 meters deep, and 700 meters high. A massive block of iron. That would weigh that amount. And that is the force between these 2 droplets of water when you're talking about electromagnetic force. So this illustrates how strong the electromagnetic force is compared to gravity. We know these 2 drops have negligible gravity pulling them. But based on the weight of the Earth and the radius of the Earth, we've now calculated that these 2 drops of water, the force between them is so many kilograms in the form of weight, or the form of weight, and it's equivalent to this block of iron. It's also equivalent to, for example, seawater, 1 kilometer long, 1 kilometer wide, and 2.5 kilometers deep. That volume of seawater roughly also weighs so many kilograms. So now we know what the force is between these 2 droplets of water. And that's BullWithBoone for this week. Thank you.